Let's talk about linearization. Here's some function f of x that I've written in red. And here is some x value, x equals a, and here's f of a right here on the red line. Now, in the past, we have found tangent lines at x equals a by finding f of a and f prime of a. F prime of a is the slope of the tangent line at x equals a. Well, what we're going to do now is we're going to use that tangent line to approximate other function values relatively close to a. Now here's the actual wording for this. L of x, our linearization centered at x equals a, is the linear approximation of f of x, and it is centered at x equals a. The reason why it's centered at x equals a is because x equals a is what defines that linearization, that model right there. I could have chosen this particular x value or this particular x value. It really all depends on what approximation you want. Now, let's talk about what we'll be doing in these problems. Take a look at this function value right here, a little bit to the right of a. You'll notice that our linearization, L of x, is pretty close to that point right there. That's what makes L of x a pretty good approximation for the function value. Although, keep in mind that we have to be relatively close to a. So we could go a little bit to the right of a, like 0.1 to the right, or 0.2 to the right, or maybe even 0.3 to the right. Or we can go like 0.1 to the left, 0.2 to the left. You see it's still pretty close to the left. That's where the center of our linearization is, x equals a. However, take a look. As we get further away from a, we have all of this loss of accuracy over here. This huge gap represents a loss in accuracy. So the closer you are to a, the more accurate your approximation is. The further you are away from a, the more of a loss of accuracy you have. So once again, L of x, my tangent line at x equals a, which we also call the linearization, or the linear approximation, that is going to approximate other function values relatively close to a. Let's take a look at a problem. Given f of x equals x cubed, approximate f of 2.1 using a linear approximation. Then check your accuracy. What we are being asked to do here is approximate 2.1 cubed. Now 2.1 cubed, I have no idea what that is in my head, and I'm sure that you don't either. But you might have a calculator handy so you could figure it out pretty easily. But let's say you're on a desert island and you don't know what 2.1 cubed is. Well, you can use a linear approximation to do this. So there are two things that we need for a linear approximation. Number one, we need a point for our tangent line. Number two, we need the slope of our tangent line. Now, before we find the point for our tangent line, we need to take a look at where we are approximating. We want to approximate 2.1. That means that we want to have an x value relatively close to 2.1 that we can easily figure out. Obviously, we're going to use 2. So we're going to find the tangent line at x equals 2. Or in other words, in this case, we're going to find the linear approximation centered at x equals 2. So let's find our point. Our x value is 2. If you plug 2 into x, we get 8. So our point is 2, 8. Now let's find the slope of our tangent line, which is given by f prime of 2. But let's first find f prime of x. F prime of x is equal to 3x squared, which means that f prime of 2 is equal to 2 squared is 4 times 3 is 12. All right, so we now have a point, 2, 8. We have the slope of our tangent line, which is 12. We can now find our tangent line. So we have y minus y1 equals m, which is 12, times x minus x1. And we're going to rewrite the linearization centered at x equals 2 by rewriting y as L of x and moving 8 over. So L of x is equal to 8 plus 12 times x minus 2. All right, Now that we have found our linearization centered at x equals 2, mainly 8 plus 12 times x minus 2, we can find L of, let's see what we're trying to find, yes, L of 2.1. We were trying to approximate f of 2.1, which is really 2.1 cubed. So here, all we have to do is show that f of 2.1 is approximated by L of 2.1, which is equal to 8 plus 12 times 2.1 minus 2. Well, 2.1 minus 2 is 0.1 times 12 is 1.2 plus 8 is 9.2. There we are. That is an approximation of 2.1 cubed right there. And as it turns out, if you actually found f of 2.1, which is 2.1 cubed, it's 9.261. What this means is that our approximation 9.2 is 0.061, 61 thousandths off. So our loss of accuracy is 61 over 1,000, which is not too bad actually. You know, considering that this is all stuff that we could have done in our head on our desert island, if we should choose to do that. So here we have approximated 2.1 cubed by creating a tangent line centered at x equals 2, and by plugging in 2.1 into that tangent line and seeing what came out. And it turns out that our approximation is really quite close. Now, the AP will ask you this: is your approximation higher or lower than the actual function value? Now, they won't tell you what the function value is, and this will be on the no calculator section, so you won't be able to graph it. And on top of that, you'll have no idea. So the question is your approximation higher or lower? Well, here's the trick to this. Let's call this f, and let's call this g. Now let's take a look at what happens to f and g if we take a linearization. Let's find linearization like right here. Oh look, here's a tangent line of g right here. Take a look. Our linearization is below f. Here, our linearization is above g. And the question is, well, why? Why does that happen? And the answer is quite simple. F is concave up, g is concave down. That's all there is to it. So, if your function is concave up, meaning that your second derivative is positive, that means that your linear approximation is going to be less than the actual function value. And if your function is concave down, that means that well, actually we're looking at g right now, so let me rewrite this. If g double prime is less than 0, meaning that g is concave down, that means that your linear approximation will be higher than the actual function value at g. So you take a look. It's higher. Here, it's lower. And that is linear approximation. Thank you very much for watching.